Hey there, buddy. I don't know why it stopped sharing. Maybe I wasn't sharing shit. I'm gonna guess that none of that was shown. So I'm gonna go back and do that whole previous video all fucking over again. So we are doing implicit differentiation. I'm at home with my wife. So if you hear none of the noise, it's probably her, I don't know, getting ready to beat the dog. Implicit differentiation, say we wanted to work with the top half of a circle of radius 3. The equation of a circle is x squared plus y squared equals r squared. Here, r is 3, so I have a 9. Since it's the top, we solve for y, we get y equals plus or minus the square root of 9 minus x squared. The upper half of a circle, y is positive, so we ignore the negative one, and we just get y equals 9 minus x squared. And I rewrote that as 9 minus x squared to the 1/2, so that when I did dy dx, it's a little bit easier. We bring the power down, lower it by 1, and take the derivative of the inside. So we have 1/2 times 9 minus x squared to the negative 1/2, and then the derivative inside is negative 2x. We clean it all up, and we get negative x over the square root of y minus x squared. Now, this wasn't too bad, but it can get pretty ugly, especially if this was a lot different. There is another method of getting this same answer. It's called implicit differentiation. So implicit differentiation, we start with the x squared plus y squared equals 9. And when we take the derivative of it, we'll take d dx of both sides. But every time we take the derivative of y, we're going to slap on dy dx because y is a function of x. So taking the derivative y, it's like saying y equals y of x. So y prime or taking the d dx of it has to have a y prime or a dy dx in there anytime we take the derivative. So let's say we have the x squared plus y squared equals 9. We take the derivative with respect to x of both sides. I get 2x for the derivative of x squared. I get 2y for the derivative of y squared. But chain rule, we take the derivative of y itself, we got dy dx. The derivative of the right side, the constant is 0. So we got 2x plus 2y times dy dx equals 0. We're trying to get dy dx up here. We're trying to get this. So we're going to isolate it. We subtract 2x from both sides. Now, and then we divide by 2y. We get dy dx equals negative 2x over 2y, which is negative x over y. If you come up here and grab y was right here, use this below. 9 square root of 9 minus x squared. We plug that in there. We've got negative x times 9 minus x squared. And we get this here was the same thing that we got doing it the other way. So implicit differentiation wasn't really any easier here. But there are times when we cannot solve for y. We were able to do this because we were able to solve for y up here on the circle. Sometimes you can't. There are some ugly functions, as we'll see in a second. So let's look at steps for implicit differentiation when you can't do that. First, we start off by taking the derivative of both sides, keeping in mind that y is a function of x. So if I were to do, for example, derivative cosine x, we would have negative sine x. But if we do the derivative of cosine y, first we take the derivative of sine, we get the negative sine y. And then we got to do the chain rule, move inside the inner parentheses. Derivative of y is dy dx. So there's a difference between the two. Then we rewrite the equation so that all the terms containing dy dx are on one side. Everything else is on the other side. A pro tip for this, y prime looks a lot like y, so don't use it. Use dy dx for implicit differentiation. Don't use y prime. You will confuse yourself. You will fuck yourself up. I promise you will. You may not do it every time, but you will do it. Then we factor out the dy dx. And so, like, if we have an a dy dx, where a can be some big function with a bunch of shit in it, plus b dy dx, we factor it out, we've got a plus b times dy dx. That's what I kind of mean by that. And now a plus b here is like a multiplier on it. So when we solve for dy dx, we're isolating dy dx, we divide by its coefficient. Here we would divide by a plus b. Or multiply, I don't want to use x for multiply, multiply by 1 over a plus b. Now finally, step 5 is an optional step. If you can solve for y in the initial equation easily, do so and then replace y in your solution. As you'll see in the next problem, that is not possible. So we're going to find dy dx for y when y is defined implicitly by 2x cubed plus secant y equals 4x minus y cubed. We start off following the steps. We take the derivative of both sides with respect to x. And when we take the derivative of y, we got to slap on a dy dx. So derivative of 2x cubed is 6x squared. Derivative of secant y is secant y tangent y. And then times dy dx. The right side, the derivative of 4x is 4. The derivative of negative y cubed is negative 3y squared. But since we took the derivative of a y, we're going to put in a dy dx. Then we'll gather all our dy dx terms on one side. On the left side, I've got 3y squared times dy dx. I'm moving the 3y squared to the left. I'm going to subtract the 6x squared over. 3y squared dy dx plus secant y tangent y dy dx equals 4 minus 6x squared. Now we factor out the dy dx, kind of like we did with the a plus b up here. So we got 3y squared plus secant y tangent y. All that's in parentheses or a bracket. That's multiplied by dy dx. The right side has not changed. It's still 4 minus 6x squared. We isolate dy dx. This looks funny. I'm going to change the way that looks. There we go. We're going to isolate dy dx, divide by 3y squared plus secant y tangent y. On both sides, that's what we get. Since we could not easily solve for y, we're not going to do so. This will be our final answer for dy dx. Okay. Why don't you guys try it with 4x to the 5th plus tangent y equals y squared plus 5x. Pause the video and try to work this out. See what you get. Follow what we did above. All right, I will assume you did. We're going to take the derivative of both sides with respect to x. We get 20x to the 4th plus secant squared y dy dx equals 2y times dy dx plus 5. We will gather all the dy dx terms on one side. I moved them to the left, which meant subtracting 20x to the 4th power over to the right. I've got secant squared y dy dx minus 2y dy dx equals 5 minus 20x to the 4th. Then I'm going to factor out my dy dx, secant squared y minus 2y dy dx. And then we divide by that coefficient. We get dy dx equals 5 minus 20x to the 4th, all over secant squared y minus 2y. Now, in the book, there's another section in 3.8 that says doing it to find the slope of a tangent line. I didn't make a video on that because we're going to do 3.7 here using implicit differentiation in the next video. So a slope of a tangent line at x naught, y naught, it's just replacing the x and the y with the values, and then you have the slope, and then you go back to doing y minus y1 equals x minus x1, or m times x minus x1, where m is dy dx evaluated at x naught, y naught. Okay? Well, I got it. It's the same point, so I should use x naught, y naught there. There we go. All right, that's it for this one. Now, next video, as you can see from the title, we're going to do implicit differentiation on inverse trig functions.